All right, if this is take two while I'm getting set up, it is being, the computer's being weird. Okay, there's that. Okay, so what we're going to talk about for this one is ideal gas law applications, which are just problems that are a little bit more deeper than just using the ideal gas law straight out. They will involve the ideal gas law, but they're going to have us think about things as we do it. Okay, so they're a little bit more involved. There's a little bit more detail going on. They're a little less straightforward. Okay. Uh, okay. So first up, let's look at this. What is the density of chlorine gas at 1.27 Celsius and 755 millimeters of mercury? Okay. I want to remind us here again. Remember, we have to know this, that PV equals nRT. Okay. Density doesn't show up anywhere in the ideal gas law. Okay. So, and there's probably more than one way to do these problems. So, if you have a different way that still works, that still uses the ideal gas law, you may be okay. Um, but this is just how I work them. Okay. Okay. So remember, we're talking about density. Density is grams per liter for gases. So this is a mass divided by the volume. Volume does show up in the ideal gas law, so that's something. We need to have some way to get into mass. And if we think about it, right, we were given temperature and we were given pressure. So our problem here is probably moles. Okay. So let's ask this. If we have moles, can we get grams? Yes. Yes, we can. Because uh, we know molar mass. Okay. Let's see. What else do we have to do to figure this out? So that'll give us grams, but we don't know grams and we don't know volume. Okay. So what are we going to do? All right. My way to do this is we're going to say you can remember because density is an intensive property, so it doesn't depend on the amount of stuff that's there. So you can just pick a volume you like. Pick a volume, assume a volume, and we'll use that to calculate moles out of the ideal gas law. Okay. Now, it's going to be advantageous for us to pick a specific volume. Okay. But you can really pick any volume you want. I am going to assume that we have 1 liter total. Okay. This will be nice because our answer is going to be grams per liter at the end. So if we pick 1 liter, we can just leave it as we'll solve for grams, and then the grams is equal to the grams per liter. So when we round for sig figs, we'll just change the unit from grams to grams per liter, and that will work out just fine. All right, so let's take a stab in this. Remember, we're going to have to change units around here. So let's fix our Celsius. So this is T equals 1.27 Celsius plus 273.15 means our Kelvin temperature should be 274.42 Kelvin. All right. We don't have to change our millimeters into atmospheres unless you really want to. You'd have to show your work for that because we have this. It's almost exactly the same color. This value of R. Remember that a torr is the same thing as a millimeter of mercury. So we can use this value here to get us through this. Okay. So what we're doing is we're assuming 1 liter and we're taking ideal gas law and we're going to solve for N. And we're going to say N equals PV over RT. Right? So we divided by RT to get N by itself. And then I flipped the whole thing over just to have it look nice. Okay. When we do that, now we can plug some stuff in. The pressure we have 755 millimeters of mercury. Volume, we assumed we had 1 liter. We'll treat that as an exact number. Okay. The R, we want to use this value because this is the units we picked. 62.37 liters times millimeters of mercury, because that's what we have, divided by kelvins and moles. And this is times the temperature, which we figured out to be 274.42 Kelvin. Okay. Now, the best way to tackle this across here is to multiply the top, multiply the bottom, and then divide your two answers, just because calculators can be weird sometimes. Everything cancels out to give us moles. So what we're going to say is this is 755 divided by 62.37. Whoa, that's weird. 62.37 times 274.42. I have to do this on my calculator again because my notes are in atmospheres and I didn't feel like redoing my notes. So 17115.6. This fraction itself has units of moles, and if we divide those two things, so 755 divided by that number we just got is 0. Which is the same thing I got when I used the atmospheres, which is great, 0.04411117. It's like a weird A. 1117. This is moles. All right. Now, last thing we got to do is got to get our moles to grams. What we want to remember is that chlorine gas is Cl2, because this is a diatomic dude. Diatomic dudes are going to have a friend with them. So what we need is the molar mass of chlorine. I might give you that. Otherwise, you can look at the periodic table and take 35.45 and multiply it by 2. I think I might let you do that without showing your work. That'd be great, wouldn't it? Here we go. 0.044117 moles times 70.90 grams for 1 mole. Okay, now I'm going to take the molar mass and multiply it by this thing, and this gives us 3.127531 grams. Okay, now we just have to remember we were asked for density, so we can convert this into density by saying, well, for 3 significant figures, 3.13 grams per liter, because we assumed 1 liter. Okay, that works for density, right? We can do density, right? Assume a liter, solve for moles, convert to grams, call it density. All right. Let's work another one. In this one, I forgot to superscript my degrees, but you guys can forgive me for that, right? We've got a gas at 55 degrees Celsius and 118.1 kilopascals that has a mass of 0.311 grams and occupies 0.225 liters. We want to know, what is the molar mass of this gas? Oh, shit. Okay, molar mass. What the hell? Molar mass does not show up in the ideal gas law. Remember again, molar mass is PV equals nRT. Okay, so let's think about this, remembering that molar mass is grams per mole. Wait a second here. We have grams. This grams will be that grams. Okay, grams per mole. So moles, we're going to solve this dude for moles. Does that make sense? Okay, so we're going to solve this for moles. Okay, do we have all the other data? Do we have a P? There's our P. We have a V. That's our V. And we have a T. That's our T. And we have R. Well, R is over here, right? We have kilopascals. So this is our R. I didn't mean to have a line like that. This is our R. All right. So armed with that, we can absolutely do this. Let's solve our PV equals nRT. This is going to look very familiar, right? N equals PV over RT. Other things you want to do, you're probably going to stop and yell at me and say, hey, dude, you got to convert that thing, that temperature, 55 Celsius is not going to work for us. 55 Celsius plus 273.15 is 328.15. 328.15, and that's Kelvin. All right. Now that we have that, we have a pressure. This is a problem I made up for this, so let's rock and roll with it. All right, what do we got? Let's see. Pressure is 118.1 kilopascals. The volume is 0.225 liters. I could have said 225 milliliters, and we would convert that dude to liters to get to liters so that we can use the ideal gas law to do that. The R value we want is kilopascals, so that's 8.3145 kilopascals. Remember, decimeters cubed is a liter, so we can say kilopascals times liters divided by kelvins and moles. Okay, and we're going to multiply this by the temperature, which we just figured out is this, 328.15 Kelvin. All right, now multiply the top, 118.1 times 0.225 is 26.5725 divided by 8.3145 times 328.15, right? This is 2728.403. This fraction has units of moles, okay? I'm going to run out of room, so I'm going to come down here. We're going to divide those two things and get this worked out. So 26 point whatever divided by 2728 means we have 0.0097392 moles. All right. This thing should have 3 significant figures. So that's there. All right. Now we have our moles. We just need molar mass. Remember, molar mass is grams per mole. So we need grams. We were given those grams, 0.311 grams. That's a 3. Okay. And divided by the moles we just found, 0.0097392 moles. Okay. It should be a small number of moles because we have a really small number of grams. And now we're going to do that. 0.311 divided by the moles we just figured out is 31.93276 grams per mole. Okay. Then we just got to round it. This will give you 3 significant figures. So we'll round this dude and get 31.9 grams per mole. Okay. So those are our 2 big applications for this, right? You may see variations on a theme, and yes, there are more than one way to work these problems. This is how I do it. If you find a different way that gives you the same answer that works, that still uses the ideal gas law, and you show all your work in your units, I'll be fine. Okay. You can always ask me however it goes. All right. I'll catch up with you later. Let me know how you're doing. If you have any problems, I'll be here.